Welcome to The Explainer. Today, we're diving into something so fundamental we almost never stop to think about it: the mass of an electron.
Yeah, an electron has mass. We all learn that. But what is it? Where does it actually come from? It seems like such a simple question, but honestly, it gets right to the heart of what reality is even made of. And for centuries, the true origin of its mass has been a huge puzzle. Well, today we're going to explore a really fascinating new perspective, one that might just change how you see everything.
All right, so to get our heads around this, we're going to need a new tool. We're looking through the lens of a model called the Harmonic Scale Framework, or HSF for short. And you should really just think of it as a completely new way to picture the universe.
So forget everything you learned about tiny particles zipping around like little billiard balls. HSF says nope, that's not it. Instead, it asks us to imagine the universe as, well, as a kind of symphony. It sees all of reality as a set of structured, interacting waves that are all flowing through different channels.
So if everything is a wave, then what's a particle, like our electron? Well, in this picture, it isn't really a thing at all. It's a stable, resonating pattern. You can think of it like a persistent note being held in that cosmic symphony, a standing wave that just holds its shape.
Okay, and this is where it gets really cool. HSF says that an electron's energy isn't just one lump sum. It's split across different channels, kind of like the different notes in a musical chord. You've got one channel for its basic wave existence, another for its familiar electromagnetic energy. But the one that's super important for our story is this third one. It acts like the electron's own personal rechargeable battery, an energy depot. And that depot is the key to this whole mass mystery.
So here's the crucial insight, the real linchpin of this whole idea. An electron's energy isn't static. It changes dramatically depending on its environment. We have to look at the two different lives an electron can lead, one where it's roaming around freely and one where it's bound up inside an atom.
Now, HSF proposes this really beautiful idea called the mirror principle. Just look at this comparison. When an electron is free, its external wave energy is cranked all the way up to its maximum, but its internal energy battery is at a bare minimum. But when it gets captured by an atom, the exact opposite happens. Its external wave energy plummets, and that lost energy gets perfectly transferred and stored in its internal depot. They perfectly mirror each other.
And check this out. This isn't just a vague concept. We can see it in the actual numbers. This table shows what happens inside a hydrogen atom. When it's bound, the electron's external wave energy hits rock bottom, and at the exact same time, what happens to its internal battery? It gains an extra 13.6 electron volts of charge. Now that number is precisely the known binding energy of hydrogen. It's no coincidence. The energy doesn't disappear, it just moves.
All right, so all of this is building up to the main event. This perfect mirroring of energy isn't just some neat little observation. It gives us a stunningly direct way to calculate the electron's mass from scratch.
Because we know exactly how much energy gets shifted into that internal depot, it creates this direct mathematical bridge. It connects the tiny, well-measured binding energy of an atom to the enormous total mass energy of the electron itself. It's linking two values that, before this, nobody really thought were directly related.
And here it is. This simple, elegant formula just pops right out of that mirror principle. It says that the electron's rest mass energy, yep, the famous mc² part, can be calculated with this surprising simplicity. There are no complicated theories, no fudge factors needed, just this beautiful relationship.
So what's on the right side of that equation? It's not some big mystery. It's built from two of the most precisely measured values in all of physics. E1, that binding energy of hydrogen we just talked about, and alpha, the fine structure constant. Alpha is one of nature's fundamental numbers. It's about 1 over 137, and it basically sets the strength of all things electric and magnetic in our universe. So, what happens when you plug those two known values into the equation? You get about 511 kiloelectron volts, and that number is the experimentally confirmed rest energy of the electron. It's not an approximation, it's not close, it's the right answer. And we got it just from looking at the energy shift that happens when an electron gets trapped in an atom. That is pretty wild.
Okay, so getting the right number is amazing, but what this implies is even more profound. If an electron's mass can be calculated this way, it forces us to ask a much bigger question. What is mass really?
This quote from the research just sums it all up perfectly. The whole process of binding an electron simply shifts energy from its external waveform into its internal depot.
Then freeing it just reverses that process, draining the depot back down to its minimal, stable rest load.
And that minimal, stable rest load, that is what we call mass. So in this view, mass isn't some intrinsic property an electron has. It's simply the baseline energy it carries in its internal battery, just to exist as a stable, free particle. Mass is stored energy.
So the next time you think about the solid, fundamental building blocks of our universe, I'm going to leave you with this question to chew on. If something as basic as mass is just a form of stored energy in a resonating wave, what other fundamental concepts might we be looking at completely backwards?